So welcome all. This is week 7 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So this week's content is based on week 7 content of the course. So more or less we are going to talk about regularization and regularization specific to deep learning. So I won't go into the derivations that professor has discussed. You can refer to those videos for like looking at it again. Okay, so I'll give an overview of how these regularization techniques can be used in practice. Okay, so before that, we'll just look at some important terms like bias and variance. So when we talk about regularization, it is very important to understand what is bias, what is variance, what is overfitting, what is underfitting. We'll just have a quick look at it. Okay, so so when you have some data set given with you, so what is the like go-to way? So how do you start? First of all, you split your data set. Like this is applicable for any machine learning or deep learning method in general. So you begin with some data set. You split it into trained data set, validation set, and test set. So you train your model based on this trained data set. What do I mean when I say that you train your model based on this trained data set? I mean that the weight update that you do is using this split of the data set. So the gradient that you're going to calculate is based on this split of the data set if you're using gradient descent algorithm. Okay. Then comes the validation data set. This validation data set is used to hypertune your hyperparameter. So tune in your hyperparameter. So you can use a small, so this percentage of validation as well as test data set is small as compared to training data set in general. So there are some regime like few short learning or for example, zero short learning, where people restrict the size of their training data set and not their validation or test. So they have a very small training data set in these kind of cases. But these are very specific examples. In general, your training data set is much larger as compared to validation and test data set. So validation data set is used to tune your hyperparameters. And your test data set finally is used to evaluate the performance of your model. Okay. Okay. So one more thing, like if you guys have any doubt at any point, you can either type it in the chat box or you can unmute yourself anytime and speak. Okay. Okay. So when we talk about bias and variances or regularization in general, so there is an underlying assumption that we make. Okay. So what assumption that we make is, so the data set that we collect in real world or the data set that we have collected, we assume that the data set might be slightly noisy. Okay. So let's say you have some pair of x I comma y I. This follows some distribution. They have some joint distribution d star. But there is a possibility that the data set that you collected or you obtained is not exactly d star, but a noisy variant of d star that you can represent by d tilde. Or in simple words, let's say there is a possibility that your x is so your, let's say your original x is x star. So what you have obtained is something like x star plus some noise, or there is even a possibility that y that you have obtained is some y star plus some noise, where these noise can follow some distribution. Okay. So generally people assume this to be standard normal distribution because your analysis becomes easy, but this can be any arbitrary distribution that you need to sort of estimate. Okay. So getting back to what we were talking that when we talk about regularization, bias and variance, what we implicitly assume that the data set that we have assumed, that we have obtained, is noisy. So this assumption is not actually incorrect, because in reality, when we collect data, there are many sources of noises that can creep in, and the data set that we obtain is noisy. Okay. But there is an extra assumption that the validation and the test data set that you have, they are clean. Okay. So what does that mean? That they represent true distribution. So the noise level over here is very small. I would just like to mention that the noise is very small in training also. Okay. So what does this mean is that your training data set and the test data. So test data is the real world data on which you want to perform your actions. Okay. The distribution of this training data and the distribution of this test data need not be exactly same. So they are approximately same. Okay. So if we just keep on decreasing the loss on the training data set, okay, it is not necessary that we will do well on this test data set as well. Okay. So this is one thing. Another thing is, let's say the data set that you collected, your training data set, the training data set is your true distribution, let's say. Okay. So like, you are sure that you didn't make a lot of errors, you have collected a very good quality data set. Okay. So then also there is a possibility, for example, let's say this chat GPT. Okay. Or there have been many, like there is a website called remove.bg. Okay, there is a website called Historica. You might know about these websites. So this chat GPT, let's say, if it was just trained on the US data set, okay, or remove.background website was just trained on images of white people. Okay. So there is this Historica app. What does this do? It will convert your photo into a small video, so live photo kind of a thing. So let's say this was also trained on white people only, because data is in India we don't have a lot of data available with us. We don't like to. We actually don't have a lot of data where we want to train these things. So let's say this is trained on just for white people. So the output that it would be giving, even if we feed in some Indian sort of images, or for example, in case of Chat GPT, like let's say the US English is slightly different than in the Indian English, right? So if we use our English to give input to the Chat GPT, then it might not perform very well. Let's say, okay, when in the case when your training data, so you have fitted very well to your training data set. Okay, let's say for Chat GPT, you just trained it on the US data set and you fit very well on the US data set. So when you release it to the world, let's say some Indian person is giving it some input, Chat GPT might not perform very well on it. Okay, so what we want is, like, even during the test time or during our application, if we have slight variation in the input, because both of us would be inputting English only, right? But there might be slight variation in the English, then also your model should perform well. Okay. So, so what do you want to do? So in these cases, what you want to do is that you should have some generalization property in your model that you are training. Okay. So for this purpose, people use something that is known as regularization. So I have tried to motivate it via two things. One is that your training data itself was slightly noisy. Then you want to regularize so that it does not fit to the noisy data set. Second thing is that your the data points that you are encountering during the testing or the real world application, that might have slight variation as compared to what you have trained it on. Okay, for that purpose also you might need regularization. Okay, any doubt till this point? Then we'll move to bias and variance. Like, what is the need of generalization? Why do we do these kind of things? I tried to motivate it using two examples, so let's see. Okay, let's get to something known as bias and variance. Okay, so here I'll be making one assumption. Okay, let's erase this pink line for the time being. Okay, so let's say you have some function f. So this curve that you see, this black curve, this is your function f. Okay, and so you are sampling some data points from it. So you are sampling some training data points from it, and you want to estimate the shape of the curve. Okay, this is the task that you have. Okay, so let's say this is your x and this is your y axis, right? So given some x, you want to predict some y. For that, you want to predict the shape of the original function. Okay, so what happened is that, let's say we have sampled these points. Okay, so you can see while sampling, we can make some slight error. Okay, for example, here the points that we have obtained is not exactly on the curve, but slightly above or below that curve. Okay, now we don't have access to the original function from where we have sampled our data point. Okay, we only have these training pink points that we have, and what we want to do is we want to estimate what is this original true function. Okay, let's say we want to search over only linear lines. Okay, so what we would get is something, this solid line that is I'm drawing. Okay, so it is already drawn, I'm just highlighting this line. So the line that would fit to this pink line would be this sort of this line that we have drawn over here. Okay, so this is one thing. Okay, so you can see that there is some error. So this much area is the error that we have made. Okay, okay, so just remember that we will be making some error if we just search over a linear line. Okay, I'll just formalize these things. Let's look at this for the time being. Okay, now what we do is, so we sampled some pink dots. Let's call it as one instance. Okay, so what is one instance? So we sampled some points and we found the best fit line for that particular sample. What we do is we repeat 50 instances of the same thing. Okay, so what we do is, let's say there were these 20 pink points that we sampled. So what we will do is we'll sample these 20 points 50 times. Okay, so not only once, we will sample it 50 times, and for every time. Okay, just give me a second. Yeah, okay, so for every time that we have sampled, we will have a line that will fit to that particular set of samples. Okay, or that particular training data set. Now what we will do is we will sort of plot those lines. Okay, so we have 50 such instances, and I have just not I have actually taken this from slides prepared by Professor Preeti Jyoti from IIT Bombay. So she has just plotted these 50 lines that she obtained on 50 instances. Okay, now based on these 50 curves that you obtain, we have two definitions. One is known as bias and another is known as variance. Okay, let's look at what does this bias means. Okay, okay, okay. So now this was our f of x. Okay, and out of these 50 lines that we had, we take the mean of these 50 curves. Okay, so let's say this is my mean that I represent by g of x. So I fitted 50 curves to 50 different instances. Now I have taken the mean prediction, that is the mean curve of these curves. Okay, I can see that there is some error between the mean curve and the original function. Okay, so the expected error, so there is some error. The expected error is something that is known as bias. Okay, so I'll just say, so what is bias? Bias is the expected value of f of x minus g dash x. So bias is a measure of how far is my true function from the mean prediction. Okay, this is what is known as bias. Okay, now let's try something else. Okay, so we fitted sort of these linear curves. Let's say we are trying to fit some okay, so fifth degree polynomial. Okay, so let's say we sample these points. Some are here. Okay, so what kind of curve we would be getting? Let's say we, okay, no, it won't have these many. Yeah, so it would look something like this. Okay, this green line might be a curve that you would obtain if you took a fifth degree polynomial. There can be, let's say, another curve which is something like this. Okay, there is a possibility if you made some error. So if you will take the mean of these kind of curves, I think you can see that the mean prediction that you will get would be sort of close to your true prediction. I agree that there can be still some error, right? There can be some error, but if you use a higher degree polynomial, then the mean prediction, so the error that you will have would be less. So error for fifth degree polynomial would be less than the error that you would have for the linear curve. Okay, so what does this mean is, I'll take some space from here probably. So what does this mean is, like, what did I did? What I did is, I went from linear curves to fifth degree polynomial. Okay, so what I did is I increased the complexity of my model. So what I'm trying to say is, if you increase the complexity, okay, So if you increase the complexity, what does that mean? So increasing complexity means your bias will decrease. Okay. So as your complexity increases, your bias decreases. Okay. And what is underfitting and overfitting? So I'll just look at what is underfitting and overfitting, and then I'll get back to what is written over there. So I think most of you know what is underfitting and overfitting. I'll just give you a very small definition. So what is meant by underfitting is, for example, in case of this linear curve, because your search space was just a linear function, you were very far away from the data points that you sampled. So your training error is quite high. Okay. So this kind of situation is known as underfitting. Okay. So underfitting means not fitting very well to training points. So you don't have capability of fitting very well to training points, and that is something that is known as underfitting. So overfitting is exactly the opposite. In overfitting, you have very small losses, so very small loss on training point. Okay. So because you have very small loss on training point, you sort of do not that great on the test point because you have fitted a lot to the training point. Okay. This is one thing. So you might know the relationship between, so if you have a more complex model, what does that mean? So that means is there is a high chance that your model will overfit. Okay. So model complexity is directly proportional to overfitting. So if your model complexity increases, you might overfit. If the model complexity is low, you will underfit. Okay. So now let's relate it to bias, and let's find a relation between bias and overfitting. So I said that if your model complexity is high, okay, so if model complexity is high, what does that mean? That means that your bias is low, right? And that also means that you are overfitting. So what does this imply? This implies if your bias is low, you are overfitting. And vice versa, if your bias is high, you are underfitting. Okay. So bias is sort of inversely proportional to your overfitting. Okay. So let's see how does this sort of behave. Okay, we'll go to what is variance. Right now, let's look at bias. So this is a graph of model complexity versus bias. Okay. So if your model complexity is low, this green line is your bias. Oh, sorry. This orange line is your bias. So if your model complexity is low, you have high bias and it sort of decreases. Okay. So we'll get back to this graph in a meanwhile after we have done variance. But for the time being, can you please guys confirm that the definition of bias is very clear? So what is bias? Bias is the error between mean prediction and the true function. Okay. So it is just how far is my mean prediction from the true function. So when we talk about mean, what are we talking about? It is the mean of 50 lines that we drew for 50 different instances. Okay. Any doubt in this? Then we'll go to variance. Like if you have any doubt in bias, understanding bias, please let me know right now. Okay, so I hope I was clear. Now let's go to something known as variance. Okay, so we talked about expected value, sorry, we talked about expected value of g of x minus f of x, where your g of x was the mean, right? And so this is something that we refer to as bias. Okay. Now, there is a possibility that curves that you are obtaining is sort of very far from each other. So what happens in that case? So if you look at the 50 different curves, and you look at its variance, okay, so that is something that is known as your variance of your model. Okay, so I'll just try to motivate it using an example. I had it here, I think. Okay, so I'll redraw this diagram. I shouldn't have drawn it beforehand. I'll just remove this also. Okay, so let's try to redraw this thing. Okay, so let's say I have some of these red data points that was available to me. Okay, so you can see that it might have come from some true distribution. Okay, and we want to estimate that thing, right? So let's say you are using a very high degree polynomial. Let's say you're using 20-degree polynomial. So 20-degree polynomial is capable enough to exactly fit to this particular data set, and hence you will have training error 0, and you will obtain a curve something like this. Okay. Now imagine next time when you sample, let's say exactly these points, you make some error while sampling, let's say this point, and you sample it to be here. Okay. Now if you will fit, let's say, a 20-degree polynomial, what would happen is it will begin on the same path. From here it will go here, then it will go here, then here, and probably this way. Okay, so you can see one phenomena, that by just changing one of my data point a little bit, the curve changed a lot. Okay, so there is a lot of error between these two curves. Okay, whereas let's say you had okay, just a second. You had similar sort of data points. Okay, and you are trying to fit some linear function. Okay, so a linear function that you would fit would look something like this, let's say. And even if you change this particular point to this now, okay, your line won't vary a lot. Probably it will sort of slightly shift here, and it will remain the same. So the error that you will have in case of a low degree polynomial among the two instances would be low, whereas here you will have high. Okay, so this phenomena we are trying to capture through variance. So if you have lot of variations between the instances, you say that your variance is high, and if you have less variations between your instances, you say that your variance is low. Okay, now you saw that when we were overfitting a lot, that kind of model, even if we change our data point a bit, it will have high variance. Okay, so overfitting means, so variance being high means that your model is overfitting. There is sort of one more thing, that if you have high complexity model, so okay, sorry, so if your complexity is high, so if your complexity is high, then also you're overfit. Okay, so we can also draw one more conclusion, that that your variance and complexity are also sort of directly proportional. Okay, so let's summarize whatever we have talked in form of this diagram. What we said is, for bias, if you increase the model complexity, your bias will decrease. So that is represented by this green line. And when you increase your model complexity, your variance increases. Okay, so in an ideal situation, what would we want? Would we want high variance or a low variance? So in an ideal situation, we would want a low variance. Why? The reason is, even if we change our training data point a little bit, that is, if there is some noise in the data set, then also your model should not change a lot. Okay, so if you have slight noise, your model should not change a lot. That's what we want is, so let me use another color pen. So what we want low variance, and also we want to fit well to the data. So we don't want the bias to be high. Okay, so our desire is also that we should have low bias. But if we look at this figure, there is no possibility that we can get both of these things together. Okay, so we sort of have to settle at something in between, where you have small variance and small bias, not the minimum bias and not the minimum variance, but something in between. So we should try to pick a model in this region. Okay, so how do we obtain these kind of things? That is the main goal of regularization. Okay, so yeah, this is the motivation for regularization. We capture this phenomena of overfitting and underfitting via these two definitions, that is bias and variances. Okay, okay, so any doubt in definition of bias or variance, or this figure that I have drawn over here? Any doubt in this? Okay, yeah, okay, okay. So there is one more plot. This was, I think, present in the slides also. So when you increase the model complexity, okay, so look at this red line. Okay, so what is happening is that you are fitting well, and your training error is decreasing, and it decreases to a very small value. But what happens to your test error? Okay, so initially it will decrease. Okay, but beyond certain point, what will happen is that you are fitting well only to your training data set, and hence you are increasing your error on the test data set. Okay, you are fitting well to the training data set, that's why you are increasing your error on the test data set. So here also we have to search for this kind of sweet spot. Okay, so this is what our search, so we'll see how we can reach here. Okay, so this was sort of motivation for bias and variance and some information related to bias and variance. Now we'll see some questions. I want you guys to answer it in chat box. Like, if you guys have understood, then you should be able to answer these questions. So first question is regarding bias and variance, which of the following is statements are true? Okay, so I want to know which are the correct options in this. We have just discussed about these things, so what does high bias mean? What does low bias mean? Can you guys please tell me what is the correct answer for this? So which of these following statements are correct? So there can be more than one correct answer also, or there might need not be more than one correct answer also. I'll wait for others' response also, then we'll see. Okay, people are saying B and C. So let's look at every option. So what does it say? That model which overfits are more likely to have high bias. Okay, so what is bias? Bias is how much error your mean line is making with respect to true function. Okay, so if your model is overfitting, then this error should be low. Okay, so this option is incorrect. So model which overfits are likely to have low bias. This is correct. Okay, so model which overfits are more likely to have high variances. Okay, so when you overfit and you change your point even by a bit, then you will see a lot of variation in your curve. Okay, so that this option is correct, and this is just the opposite of it, so both of them can't be correct, so this is incorrect. Okay, 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 so this is also sort of similar question. So what is meant by hypothesis space being richer is that you have a bigger hypothesis space. So larger hypothesis space or a bigger hypothesis space. So what is the correct option for this? So this is just related to overfitting. This does not involve bias and variance also. So statement A says when the hypothesis space is richer, the overfitting is more likely. So when your search space is large, are you supposed to overfit or underfit? That is the question. Okay. Okay. So when are you likely to overfit? Let's say if you are searching over linear classifiers, or if you are searching for classifier up to degree 5. Can you please answer this question? So when are you likely to overfit?
Degree 5, sir.
Up to degree 5, right? So which one has a larger hypothesis space? Which one has a larger richer hypothesis space? So second one is having a richer hypothesis space. So when you have a richer hypothesis space, you are more likely to overfit, right? So this statement should be true. First statement should be true, right? So when your hypothesis space is richer, you are more likely to overfit. Second one is when the feature space is larger. Okay, so let's say you have two features. Okay, and you want to fit some linear classifier. How would the linear classifier look? So this would be w1x1 plus w2x2 plus some bias that you would have. Okay, so how many parameters you want to learn? You have to learn 3 parameters. Okay, now let's say your feature space has 5 features. Okay, so then you will have w1x1 plus w2x2 plus w5x5 plus b. You will have 6 parameters to learn. Okay, now because you have more parameters to learn, your hypothesis space become richer, or it became larger. So if you have a larger feature space, then also you are more likely to overfit. So this statement is also true. Okay, so option B is correct here. Both of these statements are true. Okay, again, like if you are using it for some application, you need to check like how large is large for you. In real world application, 5 features won't ever lead to overfitting. It will always lead to underfitting. So based on your application, you have to decide what do you mean by large. Is 1,000 large for you? Is 1 lakh large for you? That will depend on the application that you're working with. Okay. Okay. Again, this I think this question is repeated. Yeah, we can ignore this question. Okay. Okay, here is another question. Which option do you think is correct? There is only one correct option, I think, in this. So what happens as the amount of training data increases? So you can think of it in two branch, like what would happen to training error and what would happen to generalization error. So a techie, so what happens? What decreases? This decreases or this decreases? Okay. So when you have large training data set, what would happen is that your training error will usually decrease. That is correct. And hence your generalization error will usually increase because you are now looking at more number of data points. So even if you have some noise in small number of data set, you can overcome by looking at other data points. So first option is correct over here. Okay. Okay, I think we have one more question over here related to this thing only. So the question is, we generate the data using the following model. So this is your true distribution. Okay. And they're trying to fit two different models. First is, let's say this is G1, this is G2, or model 1, model 2. It is asking you which one has higher bias and which one has higher variance. You guys think about for a minute and answer which is correct. Okay, somebody said 1 and 2. Let's see what other things. Okay, other person also thinks 1 and 2. Okay, so one thing we can say that the complexity of model 1 is less than complexity of model 2, right? So how was the graph that we had? So this was the curve for bias and this was the curve for variance. So as the complexity increases, bias decreases, right? So model 1 would have higher bias, right? This is correct. So this option goes out. Okay. Second thing is, as your model complexity increases, your variance increases. So model 2 should have higher variance. So this one goes out. So 1 and 2 is the correct answer. Okay. So here is a question. So somebody is trying to fit a polynomial model of different degrees on a given data, and they have plotted training and validation errors for you. Okay. So which of the degree polynomial should they use? First of all, which one do you think is the training error and which one do you think is the validation error among these two? That you need to decide. And then you can tell me what is the degree of polynomial that that person should use to behave well or to fit well to the given data. Okay, somebody has said degree 3. Yeah. So one thing that should be clear is that this blue line is your training loss because as you're increasing the model complexity, this loss is decreasing. Okay, and your orange line is your validation loss. Okay, now you see that in this region, after this region, the loss is increasing, the validation loss is increasing. Okay, so we want a degree in this range, and that degree 3 is the correct option. Okay, okay. Any doubt till this point? Okay, so we have talked about underfitting and overfitting. Okay, so first question that we should try to answer is, like, how do we overcome underfitting? Okay, so I haven't prepared anything for here, but I'll just try to write whatever options come to my mind. You guys also, if you have some techniques, you can type it in the chat. Like, how do you guys think that we can overcome underfitting? Okay,
Increase the model complexity.
yeah, that's the number one option, that you should increase the model complexity. Anything else that we can do to overcome sort of underfitting? Uh, right now, nothing is coming to my mind except for this. So I'll include if something comes to my mind. Yeah, you can add
Can
more
you,
features. Yeah, this is also correct.
can you use L2 regularization?
That would come to overcome overfitting, not underfitting.
Okay.
Okay. So we can add more features, right? Okay. So if you add more features, you will have a larger subspace and you can overcome this thing. Okay. So these two are correct. Now the main focus would be on how to overcome overfitting. Okay. So for that, there were few methods that were discussed in the this week's content. So we will look at those methods. First one is known as L2 regularization. Okay. So I'll very briefly go over all these things. So it is 6:53. This is a 2-hour long lecture. So what we can do is we can take a 4-5 minutes break, and then we can go through these techniques one by one. Okay. So let's take a 4-5 minutes break, and let's meet at, let's say, 6:57 or 58. Let's meet at 6:58. We'll continue from here only at 6:58. Okay, we'll start again. So the question is, how do we overcome overfitting, right? So one thing that we saw is, like, when do we encounter overfitting is if you have high model complexity. Okay. Or in the other words, what we can say is, if we allow our training loss to become small, or we can say very small. Okay. So what actually these methods do is, let's say if you allow models up to degree 5, so it sort of search the best degree 5 polynomial which will have minimum loss on your training data set. Okay. So the motivation behind all these methods is, if you can restrict this search space, let's say you're saying that you're allowing polynomials up to degree 5 is let's say your bigger search space, and now you say that you will allow only those polynomials for which the coefficient of x to the power 4 is 0. Okay, so this will shorten the search space for your optimization. Okay, so this is the idea of regularization that we are going to use for almost all these methods, is that we are going to shorten the search space. Okay, so we are going to reduce the search space, and the first method, that is very common method that you would have seen in machine learning, is L2 regularization. Okay, so what happens is, uh, this is your loss on your training data set. You modify your loss by adding a regularization coefficient, which is norm of your parameters. Okay, so the norm that is being used over here is L2 norm. That's why this is called L2 regularization. Okay, so there is something similar which is known as L1 regularization. So there you just add L1 norm square, and you get something known as L1 regularization. Okay, so one thing is this. So like for somebody who don't know what is L1 and L2 norm, let's say you have x is equal to x1, x2, xn, then your, okay, so this is x, not x1, then your L2 norm for your x is nothing but x1 square plus x2 square, so on till xn square, and square root of this summation. This is your L2 norm. What is your x1 norm? Sorry, L1 norm for x is modulus of x1 plus modulus of x2 plus modulus of x3, and so on. Okay, so because you have modulus over here, when you take gradient, it might be difficult in case of your L1 norm. Taking gradients can be difficult. Okay, so people use subgradients and those kind of idea, but taking gradients can be difficult for L1 normalization. One more very small comment. I'm not sure if there is any question in your assignment or not, but this is a very common question. Why does this happen? I'm not going to talk about it, but one thing that I'm going to mention over here is, if you use L1 regularization, we get more sparse parameters, sparse weight vector or parameter. So what does this mean is, let's say you have selected a model where you want to fit a degree up to 5 polynomial. So your weights would look something like W1, W2, W5 and some B. So if you use L1 regularization, there is a larger chance as compared to L2 regularization that some of your weights would be 0. Okay, so more sparse means that there would be more 0 entries in case if you use L1 regularization. Okay, this was just for your information. Okay, now when you use L1 or L2 regularization, it does a weighted scaling of parameters. So what does this mean? So let's say if W star was the optimal weight or the parameter that you obtained by minimizing L theta, and W tilde is uh, the weight that you would obtain by minimizing L theta plus some lambda times theta L2 norm square, then this whatever is written over here, weighted scaling of parameter, is a relation between W star and W. Okay, so what does this mean is, so W tilde would be a scaled version of W star. The scaling would be like reducing its length, but this reduction in length is not uniform. So let's say if you have parameter W1, W2, W3 as component of W star, so you won't scale it like W1 by 2, W2 by 2, W3 by 2. It would be a weighted scaling. So there is a possibility that you will have W1 by 3, W2 by 2 and W3 by 4, something like this. So this is a weighted scaling of your original parameter that you would have obtained. And what kind of weight does it obtain? That is very much discussed in the lecture, where you have weights like delta 1 by this plus alpha this. Okay, so I'll just change the notation. This is alpha 1 by alpha 1 plus lambda. This lambda and this lambda are same, right? Was it same? Yeah. And these alphas are your eigenvalue of your Hessian matrix that you obtain. So this thing is discussed in lecture. How does this get weighted? But what you should remember is that it weighted scaling of the original parameters. Okay. Any doubt till this point?
Sir, could you repeat that alpha portion again, sir?
So the last portion.
Yes, sir.
So I said that it is a weighted scaling of just give me a second. I said that it is a weighted scaling of the original vector, but over here I weighted it by 1 by 3, then by 1 by 2, then by 1 by 4. But in reality, what is the weight, so weighting factor that you obtain? That I think I'll just confirm it, but as far as I remember, it is of this form only. I'll just confirm for a second. Give me a second, I'll just confirm. I have it written. Just give me a second. This alpha I think is same. I just want to confirm whether this alpha is same as that, or there is some. Okay, this is same. So the factors that you have is actually so this is alpha I divided by alpha I plus lambda. Okay, so where this lambda and this lambda are same. Okay, the lambda is your hyperparameter that you have chosen. Alpha i's are eigenvalues of your Hessian matrix. So Hessian matrix is your this for your loss with respect to the parameters that you have. Okay. So this is what I said, like these weights that you would obtain, by which factor it would get multiplied is this. So let's say you have n eigenvalues that you have obtained, then your weights would depend on those n different eigenvalues. I hope I was clear. For more details, you can look at the derivation. I'm not covering the derivation here. You can look at the derivation there. Okay. So let's go to something known as data augmentation. So when I was motivating regularization, I sort of talked about two problems that we have because of which we want to do regularization. First one was that the data set might have some noise and we don't want our model to overfit a lot to our data. And to overcome that, we have proposed one regularization, that is L2 regularization. This will this will sort of restrict my data to overfitting exactly to the training point, because we have restricted the search space by imposing the condition, by including this term in the loss function. So the values of theta would be small now. So we have restricted the search space. So we are restricting the training data set to exactly fit to the, so model to exactly fit to the training data set. The second problem that I said was the example that I gave related to ChatGPT is that there can be some variants of this training data set that we might encounter during testing. How do we overcome that? So here the example that the professor has taken is, let's say he has a data set containing 2's written. Okay. Now there is a possibility that somebody writes 2 like this. So I also, when I'm scribbling, I'll write 2 like this. You can see the orientation of this 2 and this 2 is different. Okay. So this is slightly tilted when I'm writing. Somebody might have habit of writing 2 more tilted. Okay. So let's say initially you had this kind of 2 available in your data set. So what data augmentation says is, you can include variants of your data points by adding some sort of noise. For example, in case of images, you can include data points by rotating it, let's say by some degree. Okay. Or you can shift it vertically. So you have shifted this downwards. Earlier this black patch was in center. You can shift it horizontally. You can change the pixel colors maybe. Okay. Because there is a you can motivate it by example where you are training just on black and white images. So black and white to MNIST data set, and you want to predict the numbers even in colored format. Okay, that is also a possibility. There can be that the image that is clicked is slightly blurred and you want to learn even for that kind of data set. So you make these kind of variations for your existing given training data set, and you include it as your training data set. Then the model that you will learn would be sort of a more real representation of the real world data that you're going to encounter in future. So this is something known as data augmentation. This also sort of serves as a regularization technique. Okay. 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 Another technique is, like when we don't want our data to fit to a training data set, is that we can add some small noise to our training data set. Okay. So this noise can be at two places. Either you can add it to the input data set. So for example, if X was your original data set, you can modify your X as X plus epsilon, where epsilon is some normal distribution with zero mean and standard deviation sigma. You can add this noise. Also, you can add noise to the output. Okay. So for example, if you have this digit classification task, so your Y would look something like 001, because this is for 0, 1, 2, 3, 4, something like that. So you will have 1 at the position for 2 and 0 everywhere else. Okay, what you can do is you can convert this to something like epsilon by 9 at rest of the places and 1 by epsilon at 2, where epsilon is a very small positive number. Okay, so what will this help you achieve is that you won't be overfitting to your training data set. Okay. Okay. There is one more technique that is very common, that is known as early stopping. Okay. So this method is common as you can use it with other uh, regularization technique also. So it is not necessary. So what I'm trying to say is, like if you are using early stopping, you can use it with L2 regularization. You can use it without L2 regularization, and you can also use it with L2 regularization. Okay. So what does early stopping suggest is that like when you are training your model, what you do is you calculate loss on the training data set and you make update. So what does early stopping suggest is when you are calculating error on your training data set, along with that, you also calculate error on the validation data set. Okay. So you tune your parameter just based on your train data set, but the error that you are calculating, you can calculate on both the training as well as the validation data set. Okay. And what does it suggest is, like if your validation data set is decreasing, and certainly it becomes constant or it has started sort of increasing, then you can stop there, stop your training there, and say that you have started overfitting and I'll stop my training then and there. So this is another form of regularization. So there is a specific method by which you can implement early stopping, that is K minus P method. Okay. So let's say you are at kth iteration. Okay. And so I have, I think, example also. Yeah. So this P is also known as patience parameter. Okay. So let's say you are at kth iteration. What you will do is you will look at validation loss from K minus P to K. Okay, so you look at this stretch, this thing that I highlighted in yellow. If you observe that your training, sorry, the validation loss is decreasing, or it has become constant, then you will stop your training at kth iteration. Okay. So here is an example. This is sort of very similar to what you have in this year's assignment. I just changed one value over here. Okay. So let's say these are your training errors and this is your validation error. You can clearly see that your training error is decreasing. If you have, let's say, patience parameter 2, it is asking you when you should stop training. Okay. So let's say we look at epoch 1. So we can't go back. So we'll just continue over here. If we look at epoch 2 and the patience parameter is 2, so I'll look at 2 minus 2, right? Yeah. So I look at these two loss. I see that my validation loss is also decreasing. So I'm fine with it. I'll continue my training. When I come here, I look at the last two. So I still see that my training loss is decreasing. I'm fine with it. When I come here, I still see that my training loss is decreasing. I'm fine with it. When I come to fifth epoch, I see that my training loss has sort of become constant. Okay, so what I'll do, I'll suggest that after 5 epoch, I should stop my training. So this is the idea of early stopping. Okay. Okay. Any doubt till this point?
No, sir.
Okay. Thank you. So I'll go for something known as ensemble method. So the idea behind ensemble method is, okay, let's say I train one model using some data set. I train a model 2 using some data set. So let's say that model 1 is making error on some specific test points and model 2 is making error on some specific test points. What if we combine the prediction of both these models so that the overall picture that we get does not make error on lot of test data points. Okay. For example, let's say you train a model 1 as logistic regression, you train model 2 as your SVM and model 3 as your naive Bayes, and you obtain output from all these three, and if two of them is saying that your output is 1, you predict it as 1, otherwise you predict it as 0. Okay. So this kind of method is known as ensemble method. So it is written as ensemble, but many people pronounce it ensemble. I'm not sure which one is the correct pronunciation. So there are two ways to implement this thing. Okay. One is that you take the same data set as in this picture that we have drawn. So you will have the same data set, okay, but you will pass it through different kind of models. Okay. So you will pass it, let's say, through logistic regression, you will pass it through SVM, you will pass it through naive Bayes and see this behavior. Okay. So if you talk in terms of deep neural network, then what will you do similar to this thing? So you can have, let's say, if you have 3 input, you can have architecture 1 where you have hidden layer as 4. Okay. I won't draw all the lines. It is, yeah. Okay. Just see that I have, just imagine that I have drawn all the lines. Okay. And there is another possibility where you have only 2 right layer in the hidden. Okay. So these are the two different architectures that you have. You will train your both the architectures and then take combination of both of these. You can have similar many architectures of which you want to take combinations. Okay. Another method for ensemble method is that you split your data set. Let's say you split your training data set into some batches. Okay. And you train your model 1 on some specific batch and you save the weights. Then you train your model 2 on batch 2 and you save your weight and so on. And during prediction, you just take the, you aggregate using some ensemble method. Okay. So the second method is that you will have different data set split. So here you will have only one kind of architecture. Okay, let's say this represents weights. Okay, there are some connections here. Okay, but for different batches of data set, you will have many weights that you would have obtained, and you will have different predictions based on these different weights, and you will combine them to obtain an out. Okay. Now, okay, I'll go to the next line, but let me motivate this thing. So when you have deep neural networks, okay, so generally what people use when we refer to deep networks is that you will have many hidden layers and many neurons in these hidden layers, right? So training many models and then combining them is a computationally expensive task. Okay. So even you will have to do two things over here. You will have to train different models, and then while testing, you will have to pass through all these models and then aggregate their results. So overall the process is very computationally expensive. Similarly, even if you have same architecture, you will have to train different weights, store them, right? And then while testing, you will have to pass it through all these weights separately and then aggregate them. Okay. So the classical ensemble method is not very great computationally for your deep learning methods. Okay, we will do something known as dropouts, which are similar to your ensemble, but smarter way of ensemble for deep learning methods. Okay, that we'll do in a while. Okay, so the question that I've written over here is, when does test error reduces for ensemble method? Okay, so let's say I was using just SVM, okay, and I was making some 10% error. Okay, now when I use these and when I was using, let's say, logistic regression alone, then also I was making 10% error. Naive Bayes alone, also then also I was making 10% error. Okay, but when I combined all of these, let's say I am only making 4% error. So what could have happened? So this is the question. So one possibility is the places where this logistic regression was making error, this 10% point, I can make correct prediction at these points only if these two are making correct prediction at those points. Okay, so the points at which the logistic regression is making error, SVM and naive Bayes should do good on those points. Then only I can reduce my overall test error, right? So the answer is the errors of the models are independent to each other. Okay, so that means that the error at which the points at which this logistic regression is making error is independent of points at which these two methods are making error. Okay, otherwise, let's say if the errors were correlated, logistic regression, SVM and naive Bayes were making error at exactly the same points, then I wouldn't have reduced my overall test error. Okay, so this is one question. I think this is related to your assignment. So error would reduce if your errors of models are sort of independent or uncorrelated to each other. Okay, so this is the ensemble method. Now we look at something known as dropout method. Okay, so what will happen in dropout method is you have a parameter called p. So p, I am not very sure what professor has used, but I'll use p as the probability of preserving a node. Okay, so for every node in your hidden layer, that node would remain in the network or would be dropped. Okay, so the probability of that node being so that node remaining in the network is p. So what is the probability of dropping that particular node? So the probability of dropping is 1 minus p. Okay, so this thing I have written is drop a node. I will be discussing with this perspective of preserve a node. So I'll preserve a node with probability p. Okay, you can also drop these input nodes. That would reduce your number of features and it will help you overcome overfitting. But you should take care that you shouldn't use the same p that you are using for hidden layer for input, because your input carries more important information. You can use some parameter q where q should be larger than p. For example, you can use p something like 0.45 or 0.5. Then you should use q something in the range 0.8 or 0.9. Okay, so you should preserve most of these inputs. Okay. Again, these things will depend on your application, but this is in general what I can say. Okay, now what actually is your this dropout method? So what you will do is, let's say you have data set D, you will divide it into batches. You will have D1, D2, D3, Dn. You begin with D1, okay, and dropping some nodes, you obtain a architecture A1. So this second architecture over here, I am referring it as A1, okay, and you update your base, update your weights based on loss on D1. So whatever loss you observe on D1, based on that you obtain your weights. But you should remember the weights that would get updated are the weights that are left in the network. So this weight will get updated, this weight will get updated, this weight will get updated. So whatever lines you can see will get updated, but the ones that I'm drawing with blue now won't get updated. So this blue to this output won't get updated. Okay, similarly, the connection between this and this won't get updated. Okay, so this is one round that you will do. Now again for D2, you will generate another architecture A2. Okay, so you will have some another architecture A2, and then you will update the weight based on D2, and so on. You can continue your learning. This method is known as the dropout method. Okay, so what it is sort of doing is, it would be aggregating the outputs of different architectures, but a different fraction of data set is being passed through different architectures. So these weights are being shared. So you need not have different architectures trained and then those being aggregated. You are training different portions of your architecture using different splits of your data set. That's how we are sort of incorporating ensemble through this dropout. Okay. Now what happens during testing times? So what will happen during testing is, let's say this node was active with probability P. Okay. Then you update its weight by P times of that existing weight. So whatever is going out of it, you update it by P times of W1. And then you pass input, and whatever output you observe, you will report that output. Okay. So another thing is, let's say if you can have different this activation probability for different nodes for different layers. You can try those kind of variants. Now let's say some node was active for, let's say, 0.5 percent with 0.5 probability or 50% of the time, and some other node was just active for 20% of the time. Then the weights of this node will have a higher weight because it is getting multiplied by 0.5 as compared to 0.2. So these weights will carry higher value as compared to that of the other node that was active only for 20% of time. Why this thing is happening? Because this node has observed more data points than the other node. Okay. Okay, so let's try solving some question on this ensemble and this dropout. I think you have similar question in your assignment. So you are given a feed-forward neural network below. How many thinned network can be obtained from it? So what I mean by thin network is, you drop out some nodes, okay, and you obtain. So for example, for this one, we can have a thin network like I have only 2 here, only 1 here, and then 3 here. Okay, so this is an example of thinned network. So it is asking how many thinned network can be obtained. So right now you just ignore that the input layer can also be dropped. You assume that your input size will always remain fixed, and you can drop any of these 6. So the question is, how many thinned network you can obtain?
64.
Okay, so others can also try. Okay, so I'll try to motivate how you can approach this question. So for every node in the hidden layer, either you can keep the node or you can remove the node. Okay, so for every node you have two choices, right? And how many nodes are there for which you have two choices? There are 6 nodes. So there are 2 into 2 into 2, 6 times. These are the number of thin networks that you can obtain. So this is 2 to the power 6, which I think is 64. Okay. So you have a similar question, you can answer accordingly. Okay. So there is this question. I would like you to read and answer the question. I'll wait for 2-3 minutes. Like if you can answer this question, then I think you can hope that you have understood the dropout thing. Naman, it would be 64 only. We discussed why it would be 64. Can you guys please look at this question? I'll wait for 2-3 minutes and would expect the answer from you. Okay, somebody said A. I'll wait for others also. Somebody has said A, so let's use telemarks to represent that something that said A. Let me also read the question. That's a good question, Naman, that we actually can't drop all the nodes, right? In practice, we can't, because then we won't be able to connect input layer to the output layer. Okay. So then I think we can remove two choices, where actually we can remove three choices, right? One is that this layer 1, all the nodes are removed, but no. I think that's a good question. We can sort of try to look at it. So let's say if layer 3, this layer 1, all the nodes are removed. Okay. Then how many choices we can have over here? So we have counted those combinations also. So here we can have 2 to the power 3 minus 1, but it's 7, right? So 7 such choices from here. And similarly, when all the nodes here are removed, then also we'll have 7 such cases, right? So, and we will have one case where uh, both of them don't have any right. So both the layers are removed. Okay. So that would lead us to 64 minus 15. I think that should lead to 49, but 49 is not an option over here. So I think the person who created the question also sort of didn't thought in the way that we should not drop off all the nodes in a layer. So I think you are correct, Naman, that we can't drop off all the nodes. And I think in the current perspective, I'm not sure whether they have considered this thing in the option or not. So I think I'm making the correct calculation. What I'm thinking is, let's say I drop all the nodes in hidden layer 1. Okay, so if I drop all the nodes in hidden layer 1, what is the number of combination I can have? So this should be hidden layer 2. So what is the number of combination that is possible in hidden layer 2, so that I am not dropping off all the nodes? Okay, so we have counted all those combination in this 2 to the power 6, right? So it can have 2 to the power 3 minus 1 options, where all the nodes are dropped in hidden layer 1, but there are some nodes present in hidden layer 2. So that's why I wrote 7 over here. And similarly, the other way around, when I have dropped off all the nodes in hidden layer 2, by keeping at least one node in hidden layer 1, that option is also not possible. So 7 from here also. And 1 is the count where we have dropped off even the hidden layers 1 as well as the hidden layer 2. So we should subtract something like 64 minus 15. So 49 should be correct answer. Do you agree, Naman? So that is not in the option, but this year I'm not sure if they have considered. I think last year the correct solution also that they gave was 64 only. I think they didn't consider this case, but you are absolutely correct. We should consider this case. So if this time there is an option where you are able to satisfy this thing, then you should take that option. If the TA marks it incorrect, you can raise it in the discussion forum. So that is one option. So now let's get back to this question that we had. So this question says that we trained a neural network using dropout technique. We observed that the weights learned by the two different neurons in the same layer, okay, is H1 and H2 are same. So the weights that they have learned is same, okay. So, okay. But while calculating the output, H1's contribution is more. So P1 times W is more than P2 times W. Okay. What does this mean? The probability of retaining H1 is more than that of probability of retaining W, because during the output we multiply it by that particular probability, right? So yeah, so contribution of H1 is more. That means H1 was retained more number of times. So that means H2 was dropped more than H1. So I think B option is the correct answer. Okay. So there are two more questions. We'll quickly finish them. So the question says we are adding a, yeah.
Please repeat the previous questions.
Okay. So what does this said is the weights that they have learned is same. Okay. So let's say they have learned weight W and W. Okay. Now what it is saying is that the contribution of first one is more than the contribution of second, right? So how do we see the contribution? So contribution was just P times the weight that they have. So where P is the probability with which that particular node was present during the training, or P is the probability with which that particular node was retained. Okay. So this would mean that my P1W is greater than P2W. Okay. So if probability of retaining is more, that means it was active for more number of batches than that of second node, right? That of H2. That means that H2 was dropped more often than H1. So that's why second option is correct.
Okay, sir.
Okay. So this question is, we are adding Gaussian noise to the input before feeding it into feed-forward network. Which regularization technique are we using? Can you guys answer? Like if I'm adding Gaussian noise, what kind of
I think L2 regularization.
okay, so we are adding noise to the input. Then what kind of regularization are we using? In L2 we would have added this term. If my weights are W, then I would have added W2 to the loss. That is L2 regularization. I'm adding noise to my input.
Data augmentation.
Okay, so here there are two correct options. First is that when we are adding noise to the input, adding noise during training is itself a regularization technique that we discussed about. We talked about adding noise to the input as well as adding noise to the output. So this is in itself a regularization technique. Okay, but when we are adding noise, we are including these noisy points also. So there is data augmentation is also correct. So these two are the correct options. Okay. So this is the last question for today, I think. Yeah. The question is, we have trained 4 models in the on the same data set with different hyperparameters. The training and validation loss for these models are listed below. Which model should we choose to get best result on the test data set? Okay. So if we look, this one has the least training error. Okay. And this one has the least validation error. And these two values are quite close to each other, 0.3 and 0.5, whereas 1.7 and 0.7 are very far from each other. So we can say that the model has overfitted for this 0.3 case because the validation error has become very large. Okay. So what is happening for this last one? So for the last one, the training error is also high, as well as the validation error is also high. So this is the case of underfitting, right? This is underfitting. Here also, if we look at this example, the training error is still high and the validation is also high. So here also we are sort of also in the regime of underfitting only. Here we can see that the training error has also reduced to some extent and validation error is least. So this is the best model that we should choose. So model 3 is the one that we should choose for getting best result on the test data set. Okay, so this first case is overfitting. First is overfitting, these two are underfitting, and this is the case that we should go for, model 3. Okay. Okay. Any doubt in today's content that we have covered?